Pretty good.
It's almost like a stereotypical there's this giant guy, and that's how he talks, and he had this yesterday.
Oh, really?
Yeah, he's in Hicks class. He showed us this thing.
Oh, yeah?
Like, what is this?
He's like, I have to
It's
memorize
a circle. You gotta remember all the things on the circle. That's literally how it sounds.
It's pretty true.
It's just 1, 2, 3, 3, 2, 1.
I like it. Well, I'm not going to sound like that.
Give it a shot.
You must remember the complication of the situation.
So, we are going to be getting into trigonometry. Now, I desperately want to make you guys, at the beginning, understand what it's all founded on. You could do so much with trig functions. You could do a stupid amount of stuff with trig functions. Silly, crazy amount of stuff. But it all is based on something really crazy simple. And if you just remember what it's based on, it'll make, hopefully, a little more sense as we move along. So here's the unit circle. So pretend like it's actually a real circle. And one thing I want you to realize is you move around this unit circle. So the reason it's called a unit circle because the radius is 1. If I'm here, in fact, let's go ahead. The big thing about chapter 5 and chapter 6 is chapter 6 talks about degrees, which we all come in knowing. How many total degrees in a circle? 360. So we all know degrees. Chapter 5 talks about things from the perspective of something called radians. So what I tend to do is I tend to introduce something with degrees, and then I show you what it looks like using radians. And as you move forward, you actually want to use radians more often. Because I don't know if you guys realize, degrees are completely made up. I mean, completely. Radians are the actual measure of how far you've gone as you move around the circle. Degrees are totally made up. Why do you think we set the degrees at 360? It's fun.
Because it divides by lots of different things.
Exactly. It's got a lot of divisors, for one thing, right? So the Babylonians actually have a number system based on 60. Our number system is based on 10. So how many single-digit numbers do we need? 10. 0 through 9. You with me so far? The Babylonians have a number system based on 60. And they did that because they understood that there was close to 360 days in a year, and they wanted their number system to mimic that because the year cycle was important to them. The harvest time and ritual, when do I do this ritual? When do I harvest this stuff? So it's all based on the year. So we actually steal a lot, like the way that we have time, the way that we break down latitude, longitude, those we all stole from the Babylonians, using 60 minutes, 60 seconds. You guys semi with me? But it also has the beauty of being divisible by a lot of different numbers. I can break 360 up in a lot of different ways. Cool. So all the way around is 360 degrees. 360 degrees all the way around the circle. That's neat. So as I start at 0 degrees, if I'm at 0 degrees, what point is this? So there's a connection between the degree I'm at. So here's my circle and I'm looking at 0 degrees. X is something and Y is something. So what is that point? 1, 0. The minute I start turning, what happens to my X value? The minute I start turning and I look out, and now if I look this way, I see this point. My X value is going to get smaller, and my Y value is going to get correspondingly bigger somehow. Right? Isn't my Y value, it used to be 0. Well, now it's actually something. Yeah. But my X value has to be smaller, of course, because I'm coming in, until finally up here it's going to be My x value is going to be 0. So up here at 90 degrees, this point is 0, 1. And then when I start going back here, what becomes negative?
X.
The x value, and the y value decreases from its maximum back down, and so forth as you go around the circle. So there's a lot of repetitions going on here. Whatever's going on in the first quadrant is basically going on in every other quadrant. That some of them have negatives here and some of them have negatives there. You guys semi with me still? So it really seems to be a study of what x and y do as I move around the circle, and that's really where we start with this idea. So let's talk about, what if this was 30 degrees? All right, and let's see. Let's kind of draw that triangle here and take a look at what's going on. Because I want to figure out what that point is there. That point was easy. That point was easy. That point ain't easy. The hell's that point going to be? I don't know how much this pulls in. I just know it's going to be less than 1. And I know this is going to be more than 0. So basically, I don't know much. Right? So I got to figure this out somehow. So this is kind of nifty. If this is 30, this is understood to be 90 because it's got to be true x, true y. They're going to be 90-degree angles to each other. And this has to be 60. So then we get a total of what inside, of course? 180. Good. Let's all start there. Cool. So 180 degrees total. That still doesn't really help me very much. All right, now pull back. Don't go there yet. Let me do something that might help us out a little bit, believe it or not. If I just put another triangle next to that, what kind of triangle is this whole thing now? Does anybody know? What kind of triangle? What's the name of it? Equilateral. Good. So if this side is x, what's this side?
X.
X. And what's this side?
X.
X. I like it. Everybody still with me? What am I trying to get here? This is a good idea. Let me pull us back a little bit and try to remind you guys what exactly it is I'm trying to get. If I'm trying to get this point, I need to know how long this is and how long that is. Because that would correspond to the x coordinate and the y coordinate. Now, are you guys kind of with me why I might be doing all this weird shit into this triangle?
No.
Okay. A few of you guys are. Good. That's all I need. So I think somebody was asking me a second ago, what's this going to be? Yeah, x over 2. And what's this here? I don't know. Let's just call that h for right now. Okay. You guys still semi with me? A little bit? All right. Now, do you notice how if x were 1, and I know it's 1 because this is a unit circle. Let's kind of redraw this now. Now, let me focus on that right triangle again real quick. This is 1, so this is 1/2. This is still, I don't know what the hell this is, right? This is still just h. But can't I solve for it now? Yeah, using what? Yeah, old Greek Jews, Pythagorean theorem. So I got h squared plus, good, 1/2 squared equals 1 squared. I love it. And then just solve for h. You guys semi with me? What do you get when you do that? So you get h squared equals 1 minus 1/4. H squared is 3/4, so h would be, yeah, root of 3 over 2. I love it. Now plus or minus because this is lengths. So we can throw out the negative possibility. So then what point is this? What's the x piece? Good. Square root of 3 over 2. And the y piece is 1/2. I love it. So let me see if you guys are able to take the next step. Let's see if we can decrease our work. The more you understand, the less you've got to do. If I'm at 60 degrees then, it's the same exact situation. My triangle is just kind of turned. You with me? I've just kind of picked that triangle up and put it there. It's the same damn situation, isn't it? Except now my x and my y have switched. Now, if x is the smaller dude and y is the bigger dude, so what's this point going to be? 1/2? Root 3 over 2. I love it. And throughout this whole thing, the specifics are nice, but it's also following what we know it's got to be. X has got to be getting smaller and smaller, and Y has got to be getting bigger and bigger. There's no other way around it. Now, there is one last angle that we want to make our basic kind of angle that you guys will eventually have to memorize this stuff. It's going to be that 45-degree angle. Just kind of focus on that 45 degree. So if I have a 45-degree angle, what's this angle going to be? 45. So this has got to be 1. That's my radius. Whatever this side is,
X divided by 2.
if that's 45, and this is also 45, they both have to open up to the same amount.
Yeah.
So if this is X, this has to be the same amount.
Yeah.
Does that make sense?
Yeah.
Cool. That idea actually helps us out with other things too. If the angle opens big, its side across should be big relative to one that's opened up small. That kind of makes sense. It's going to help us out when we get a little further along. So what can I set up here? Same thing again, right? So you get x squared plus x squared equals 1 squared. So you get 2x squared equals 1. You get x squared 1/2, so you get x equals 1 over root 2 or root 2 over 2. Is that cool? And there I just rationalize that. Yes, there will be a lot of rationalization, both the mathematical type and the psychological type, as you could say. All right, so let's summarize what we know so far and see if we can expand on it further and do even less work than we just did to expand on it. Because like we said earlier, everything that happens here has to correspondingly happen here. It's just that I've got to realize what's negative in those places. So let's summarize what we know so far. At 0 degrees, something called the terminal point. Just to use the words, the language that the book does. The terminal point would be 1, 0. At 30 degrees, it's 43 over 2, 1/2. At 45 degrees, what does this actually tell me? What's the point at 45 degrees? X, Y, yeah, they're just both the same, aren't they? Root 2 over 2, root 2 over 2. Which makes sense. Halfway through turning, my X should have decreased by the same amount that my Y increased. That's the place where they should both be the same. That really just makes sense. Halfway in between where Y is max and X is max, they should both be the same. Thank God, that makes sense. So 45 is root 2 over 2. Root 2 over 2. At 60, the reverse of this situation. And at 90, it's the other max, the other extreme so far. Now watch this. Let me show you something that's kind of cool. Oops. Yeah, I mean, that's good. Yeah. Okay. Before I go for the next quadrants, let me show you something kind of cool. Let me see, I'm trying to figure out where to put it up on the board. Here, I'll do it here. Isn't 1, couldn't I say 1, isn't 1 2 over 2? And isn't 2 root 4? Okay, now why the hell? So basically what I have then is x goes from square root of 4 over 2 to square root of 3 over 2 to square root of 2 over 2 to square root of 1 over 2 to 0. You do that again. Because you got to memorize this shit, right? You have to, believe it or not. So it starts, it's square root of 4 over 2, square root of 3 over 2, square root of 2 over 2, square root of 1 over 2, 0. That's kind of a cool pattern to realize is there. And the y's just do the opposite. They start growing. As x shrinks, the y's grow. You guys kind of with me still? Okay, cool. There's all kinds of weird shit I've heard. That's the thing I made up for myself when I was learning this stuff. And that's obviously what makes the most sense to me then. But if you've heard other things, you can share with me. Every time I teach this stuff, somebody else tells me something their teacher told them. I'm like, I've never heard of that before. It's kind of cool. So what's going to happen over here in quadrant 2? So what angle is this one going to be here? What angle is it going to be? What do you think? This angle here is going to be another 30 degrees. So this whole angle is going to be 120. So at 120 degrees, my x is going to start to grow big negative, and my y is going to start to come back down from that max. Does that make sense? Because now the y is shorter. Right? The y is definitely a little shorter. But it follows the same pattern back down. It's just that now my x has got to be negative. And my y is just going to start to go back down the same way. How are we doing so far? Okay, cool. So then the next one would be actually the corresponding 45 degree. What's this here? 180. So 45 degrees from that back would be how much? 135 degrees. Right? 45 back from that would be 135. Are you guys with me? No, but I'll keep going anyway. So I need to identify the corresponding angles in this second quadrant, and that's all I really have to do is figure out, okay, I want to be halfway there. So it's halfway between 90 and 180? 135. So that's corresponding to the 45. So 135, what would that point be? Yeah, negative root 2 over 2. And then root 2 over 2. And we could do this all the way through, but I'm hoping I don't need to. Please tell me I don't need to. Here, what's going to be true about all these points here? They're both going to be negative. Here, what's going to be negative?
The y.
The y values, not the x. I like it. Cool. Okay. Cool. Maybe. Okay. So the only difference really between section 6.1 and 5.1 is instead of using degrees in 5.1, they use these things called radians. So degrees, totally made up. Radians, totally not. Because radians are based on the actual measure as you move around a circle. So if I have a unit circle, if I have a radius 1 circle, what is its circumference? Careful now.
Oh,
That's area, because it's squared units
so
for area. 2 pi r, so it'll be
yeah, 2 pi.
2 pi. Right?
2 pi. Oh, 2 pi better than 1 pi.
Yeah, the lesser known math rapper. First time ever, I just made the jump up now. It sucks. That's all right.
You might get shot, you gotta look out.
So if I went to here, if the whole thing is 2 pi, all the way around is 2 pi. This is 0. What should it be right there then? A fourth of 2 pi. What's a fourth of 2 pi? Reduce it.
Fourth of what? Half pi.
What's a fourth of 2 pi?
Well, half a pi.
Yeah, pi over 2. So what would this be? This would be a half of 2 pi. This would be pi.
Pi.
Half of 2 pi. All the way around is 2 pi. So if I go halfway, pi. That's crazy. Right? And now I want pi.
I like pi.
Are you guys still with me?
Yeah.
Nothing amazing. Now let's stop right here and get something a little more specific going on here. Because I want to be able to translate all these little weird angles in between, and I really don't want to go, well, 2/6 pi, I mean 1/3 pi, and 1/4 pi. No, screw that. Let's get something a little more algebraic that we can do here. Pi must be the same as how many degrees?
180.
180, because it's in the same damn place. So if pi is 180 degrees, if pi radians, you throw that in. That's the units we're using here. Pi radians is 180 degrees. So these radians are the actual measure based on the true circumference of the circle. So that's why you use radians so much more often in mathematics. Because they're true measurements. Degrees totally made up. We can still use them every now and again, but we can't use them in certain situations. So when in doubt, use radians. So what does this really mean? If I had 270 degrees, how could I convert that into radians? Now, for all my chemistry folks out there, this should look very familiar. You put, what do you put down there to kill the degrees? So you put 180 degrees, so your degrees go away. And that's also known as pi radians. So now you're going to begin radians at the end. Unit analysis. Holy shit. So 27 over 18 reduces to 3 pi over 2. Good. And that would be 90 plus 180 is 270. So correspondingly here, that's 3 pi over 2. Right? A pi and a half would be a pi and a half. That makes sense. How are we doing so far? I mean, is this so far decent? A little shaky? Which is understandable. When you first get into something brand new, you got to give your brain a chance to go through it. How do we feel about this here?
Okay.
I mean, cool. I like it. That was. I wish I got that response more often. I was asking a question. Okay. So where does trig come into all this then, Jeff? Because we haven't actually done any damn trig at all yet. Right? We've just broken up the unit circle into parts and talked about the points that it's pointing to, and yay. That somehow feeds into trig. And all trig is really is just referencing these. And all those are ratios of sides of a triangle. I don't know if you guys are with me. So back when I had up here this, if I have any triangle, any 30, 60, 90 triangle, remember how we had this was x over 2? And now we know that this is root 3x over 2. We kind of figure that out. X could be anything you want it. So you can grow it, you can shrink it, but they have to be in these ratios for this angle measure. 30 degrees has to open up to half of this. 60 has to open up to root 3 over 2 times this. It's got to be those ratios. So if I had a 3, 4, 5 triangle, we don't know how to do this yet, but later in this semester, we'll figure out how to figure out that angle. And you say, did you say figure out how to figure out? I did. We'll see how to figure out that angle. That's a little better. But the point I want to make is, if I double the size of this triangle, no, Jen. Thank you. If I double the size of that triangle, does that angle change? Of course not. I just effectively went further out. So the angle doesn't care. It's like, okay, whatever. The angle's the same there. So that angle somehow is connected to like a ratio of 3 to 4, because that ratio will always be the same. You with me? So there's a connection between an angle and a right triangle. You put that in there. This is all right triangle. There's some connection between an angle and a right triangle and the ratios of sides. So all trigonometry is an attempt to formalize that, to actually make reference, make functional names that relates to certain ratios. If I say SOHCAHTOA, okay, right? Some of you who love it are going to hate my next statement. I don't like it. And you'll see why. You'll see why, especially if you're going into calculus, but even later this semester. SOHCAHTOA, I know a lot of you guys, anybody have no clue what that is? Does it sound like a summer camp? I'm a camp SOHCAHTOA, it sucks. You'll see here not too long from now. But for those of you who know what that is, I don't want you to lose faith. You can use it. I love it. Use it. But you will see how it's something that's not very useful. It's sort of like, remember FOIL?
So you have something better?
Oh, hell yeah.
Okay.
And it's not some weird little... Again, I'm not that cutesy with stuff. I'm sorry. But if you just remember the basics of trig, you don't have to have SOHCAHTOA at all. And if you look at it a different way, it's more applicable for further things. FOIL kind of sucked because it only works for a binomial times a binomial. The minute I put another thing in one of these, FOIL goes to hell. You're going to come up with some other first, outer, middle, first, inner. Screw that shit. Then you immediately let go of that. So I'm okay with this to a point, but I wish they wouldn't teach that at all. Just teach distribute. then that idea doesn't change, does it? It doesn't change. I hate when we teach something and then the idea suddenly doesn't work here, it changes, and that's when people start to lose faith in math. Why did it work there? Now it doesn't work. SOHCAHTOA is the same kind of way.
It just helps you organize your thoughts.
I know. And that's why
I don't know.
there are definitely problems
Yeah.
that approach actually is a little better than the approach I use.
Yeah.
But the approach I use gets you ready for the more advanced stuff.
People don't tell
SOHCAHTOA
you
does
not.
not.
To be like, okay.
I'll still teach you guys SOHCAHTOA, I will. And I still will let you use it. But I will always show you how the other way to look at it will be better. Will get you ready for more advanced stuff. So here's the trig, and then I'll let us out of here. Here's a little bit of trig. A little.
Probably all we can handle.
Okay. Here's our first use of this symbol. This is the Greek letter theta. So that's a letter that's very often used for angles. Either that or they use uppercase letters like uppercase A, uppercase B, right? Given this, and let's give these things names that make sense. This will be Y. This will be X. Okay, that's cool. It makes sense. You with me? And this will be, what do you think?
H.
Make it H. That sounds good, right? H for hypotenuse. So you can make it R for radius. You don't want to make it 1 because you want this to be very general. But I'm hoping you guys realize if you have the unit circle and you have everything that's true about it, it's also true, the ratios will still be true no matter how big you make your circle. In the circle are these triangles, so no matter how big you make your triangle, these ratios are still true. That was at 3, 4, 5, 6, 8, 10, that idea. So the reduction will always be the same. So for this, we define this ratio, the ratio of this side to this side. And I will say it for you SOHCAHTOA people, in SOHCAHTOA language. It does sound like an Indian tribe. We call that sine theta. So the full expression for this function is sine. So math people, we take the one letter off and we feel like it's a big victory. So it could have been almost any, again, it could have been almost any symbol that wasn't used to that point. But we decided to call it sine. And I'll get a little bit into the history later. I just want to let us out of here soon. So this is sine theta. It's defined to be the ratio of, now let me say this in terms of SOHCAHTOA. The opposite over the hypotenuse. So hypotenuse is probably not. There's your SOH, so. SOH, so. What's more useful is just this. That is much more useful. If you remember that sine goes like Y, that will get you through so much more than SOHCAHTOA ever would. How are we doing so far? Is that all right? So I really want you with me here. We've been talking all about the ratios of these sides, and that comes from these terminal points, right? So we talk about the ratios of these sides. So like here, let's look at this, 30 degrees. We had root 3 over 2 was the x, 1/2 was the y, and this is, of course, 1. What would the sine of 30 degrees be then? Here's 30.
1/2 over 3,
Yeah.
3 over 2.
Careful. It's y to h.
Oh. 1/2 over 1.
So 1/2 over 1. So sine of 30 degrees is 1/2. If you had a bigger triangle, I don't care. It will reduce to 1/2. So this is very interesting. We've defined the sine to be the ratio of those sides. So in doing that, we defined what sine of an input is. very specifically for 30 degrees, we define it to be 1/2 as an output, because that's what a 30-degree triangle looks like. When you do the ratio of those sides, that's what it comes out to be. So sine of 30, wherever the hell you have a 30-degree angle laying around, the sine of that will be 1/2. I don't care how big your triangle is, how small your triangle is. Okay, cool, maybe. Cosine, if sine likes y, cosine's probably going to like x. So in SOHCAHTOA speak, this is the adjacent side over the hypotenuse. So what do you got so far? We have sine opposite hypotenuse, cosine adjacent, ka. There's your ka. And me, one reason why I'm not cutesy is because sometimes you say SOHCAHTOA real quick and you're like, is it sakoto, ka? Screw it. I am that bad with memory. I got to do this still. Left, yes. and then here's the third one, and we'll talk about the other three later. This last one is called, oh, by the way, this is cosine, so it seems to imply that these somehow go together. It kind of makes sense that they do. Tan, standing for tangent of the angle, is defined to be y over x, which you'll notice is the same thing as sine theta over cosine theta. If you did sine theta over cosine theta, wouldn't the h's cancel? You know, if we y over, so tangent theta is also sine theta over cosine theta. Now, as I'm doing all this stuff, it's really easy to get lost in all the minutiae, but sine is defined to be the ratio of sides of a triangle. Cosine is the ratio of some other sides of a triangle. Tangent is the ratio of the last set of sides of a triangle. All of trig is based on ratios of sides of triangles. Ooh. It doesn't seem like you should be able to do a lot with that. But it's insane the amount of stuff you can do with that. But never forget, that's the basics. That's what it's based on. Everything you do after this point is based on ratios of sides of a triangle. And yes, I will say that a lot until it gets stuck in the head. So finally you see here, this would be, if it's y over x, it's opposite over adjacent. And there's finally your TOA, right? Tangent, opposite, adjacent, TOA. So there's your SOHCAHTOA. And again, personally, I don't use that very much. I think you might have picked up on that. I find it much better to use just this idea directly. So real quick, what would tangent of 60 degrees be? Remember, it's y over x. So what's the y for 60 degrees? Radical 3 over 2? 1 over 2? So the over 2's cancel, so you're left with radical 3, right? So what we'll pick up on after the break, after spring break, that is. We're not going to take another break and keep going. After spring break, we'll pick up on making a complete table, and I want to make it really clear as to what you need to memorize and know. If you're going into calc, if you're going into 180, your calc teacher is going to expect you to know this. If I'm your calc teacher, oh shit, yeah, I'm going to expect you to know trig. Normally, it's the trig and the algebra that kills people in calculus. It's not the actual calculus. That's relatively easy to tell you the truth. It's the trig and the algebra that kills people in calculus normally. Yes, sir?
What assignments does what we just learned correspond to, so we know what
It's a great question. No way. 5-1 and 6-1. Not yet. 5-1 and 6-1. And a little bit of 5-2 and a little bit of 6-2. So we just got a little bit of a baby step into these two chapters. So I will post, for those of you on WebAssign, if I forget to do this, obviously just email me. Don't send me a message in WebAssign. I don't check that very often. Send me an email. All right. So have a really good break.